good to see you all back from the break. We will start with the next session. And we are very excited to share with you more details on the upcoming guideline on reliability-based methods. It's a field that I've been working in for the last almost 20 years, so it's not an entirely new subject. But I think so far it has been mainly used in more special occasions and in very specific areas. And maybe now is the time for a more widespread use and to use the benefits and the potential of these methods. And so we want to show that to you by means of an example during this presentation. My name is Timo Schwenkebeek. I work at Deltaris in the Netherlands, as I said, mostly in risk and reliability topics in the geotechnical domain and hydraulic engineering and flood defenses. And the other speakers here are Stéphane Comment, who developed the example that we will show you, from Switzerland, Kerstin Leslie from the University of Siegen, and Johan Spross from KTH Sweden. We also would like to know who we have in the audience, at least the groups of, let's say, professionals that you represent. So I would like to ask you to raise your hand if you are a designer or working at an engineering company. That's at least half of you, I think, yeah. If you work for a contractor, construction firm, also good representation. Yes. And maybe academia, research organizations, about the same as contractors, interesting. And maybe another question to follow up, who of you has not been so far involved with the, let's say, generation of the writing and the developing of the new next generation Eurocodes? So that is almost, also almost half at least, yeah. So that's good to know for us, that we really have the engineering companies, the contractors here, and then also people who haven't heard the story before. It makes it even more important for us. All right. So let me show you how we're going to do this. I'll give you a general introduction to the topic and to the contents of the guideline. And then we will take you through a design example. And we will intermittently give you some more detailed contents of the guideline. That's what Johan and Kerstin will do, and then Stéphane will tell you, based on the example, how we dealt with those specific tasks, like defining the problem, uncertainty quantification, doing the actual reliability analysis, and so on. And in the end, I hope we have the time for some questions and discussion. So let me jump right into the topic, because we have a lot to tell you about the motivation, backgrounds, and the guideline contents. Well, the general background is that we have a lot of uncertainties in geotechnical design and the assessment of structures. We've been talking this morning mostly on the ground properties and the ground model. But of course, there's more to it. There's uncertainties in groundwater conditions. There's uncertainty in the actions. And last but not least, we also have uncertainty in our calculation models, because even though we have sort of quite good information on the input to our calculation models, we know that models are not perfect, and we have to take that into account too. And that makes that the total uncertainty is much larger than other disciplines like in structural engineering. As already addressed this morning, we are not working with controlled or quality controlled materials, but with soil. Of course, in the past, or also currently, there's been and there are several ways of dealing with uncertainty. Right? Historically, we've been working with factors of safety overall, so to speak. So you do your best guess of all properties, you get a calculation result, but then you put a factor of safety on the let's say overall result. Then what we have in the current version of the Eurocodes is the partial factor method, and we will see that that is also related to reliability concepts, because the partial factors are actually meant to cover uncertainties where they actually occur. What we're going to talk about in this presentation is reliability methods or probabilistic analysis and design. And then there are also other things that you can do to cover uncertainties, like geostatistical methods, random field simulation involving the consequences in a risk-based decision analysis, and for example the observational method. But we're going to focus on the red arrow there. So, to be on the same page on the overall concept, suppose we have a load effect model. In this case, I was showing you in the beginning in the picture uncertainties, we're calculating the bending moments in the sheet power, right? So that calculation model that we would use has a number of input variables, and in a conventional design with the partial factor method, we would feed that model with design values or with representative values depending on what you're calculating. But in a probabilistic analysis, we would give as input probability distributions to represent the uncertainty in those quantities. Could be ground properties, it could be geometrical properties, whatever is relevant. What you get from the probabilistic analysis essentially is the uncertainty in the outcome. So in this case, the uncertainty in the effects of actions in our example, the uncertainty in the bending moment calculated, and in a conventional design you could also get from that the design value. Similarly on the resistance side, you may have a resistance model, in our case for the sheet pile wall, that may be just, for example, the yield stress, but could also be a more complicated model that involves several variables. You could similarly calculate the uncertainty on the resistance side too, and then that would allow us in combination to get an uncertainty in the system response or in the factor of safety or in the safety margin. And in a reliability analysis, we would look at the probability of the exceedance of the limit state, let's say where the safety margin is 0 or where we go to a factor of safety below 1. And that probability here that we would get to failure, to an undesired state, is the probability of failure. And we can also express that in terms of a reliability index. Don't look at formulas, that's not for now. But these will come back also in terms of the reliability requirements later in the presentation. If you look into the backgrounds of the Eurocode series as a whole, there's also a whole reliability background to it. There is another guideline, which is not ours, on that specific topic, the reliability backgrounds of the Eurocodes. It's also pending publication. And what I extracted from that is that you have essentially 4, let's say, levels of types of design that you could make. You have the risk-based approach, the reliability-based approach, and the semi-probabilistic approach, or I should write just here the partial factor method. And what you do in risk is you look at probabilities and consequences to assess risk. And in reliability, you look at if your reliability is sufficient, and the partial factor method is the verification as we know it. But the relation between the different levels is that actually the partial factors are there to ensure that we achieve a sufficient level of reliability, and if we have reliability targets, they are there or they are based on the consequences of failure and to derive from that an acceptable probability of failure. Now we've seen the rearrangement of the Eurocodes, no need for me to go in detail into that. There's just 2 important things. So one is that in the new EN 1997 part 1, we will have a specific mentioning of reliability-based method, as showed this morning, and I will show you in a moment. And the other one, which will come back in a couple of examples that I will give you later, is that EN 1990 part 2 will also address the assessment of existing structures, which is a particularly interesting case for the use of reliability-based methods. We'll come back to that. So in EN 1991, as published now, here I show you the same sentence that Adrian showed this morning. Limit states for geotechnical structures shall be verified by one or more of the following methods. And then you see besides the partial factor method, there are also reliability-based methods mentioned. And you can also see that all the other methods that I mentioned have sort of a reference to different clauses or paragraphs in the code, but reliability-based methods do not. And the reason is there is not much more said in the code about how to deal with reliability methods in design or assessment. So that's why there was the need for a guideline, the guideline that we've produced for full probabilistic verification of limit states in terms of probability of failure or reliability index. So this was the objective. This is a broad outline of the table of contents. Here also we go into the relevant parts of the reliability backgrounds for Eurocodes to give you some context. Then we describe the reliability verification procedure, which we will go back to in a moment. We talk about reliability targets, the uncertainties in geotechnical design and assessment and how to characterize them, how to do reliability analysis, and then some special topics on Bayesian updating and also the relation with partial factors. So we had a little competition with the 4 guidelines here, and I think we may have won 2 of them. We produced the most number of pages. Not sure if that's something to be proud of. The thing is that this is a relatively new topic and we had to give a little bit more background than the others, I suppose. And the other one is who would publish first, and we're the first to get notified that we're ready, so the document should appear in maybe this week, hopefully. I thought that I would get an applause for that. Thank you. So into the reliability verification procedure. There's a couple of things that are just like in a normal design situation. You just take a couple of different approaches there. So in the problem definition stage, you have to define what we call in reliability based methods the limit state function. So actually how you assess whether you are whether there is failure or you are in the desired state of the structure, whether you're okay or not. And the underlying calculation models. You have to, of course, assess the ground model as you would normally do, but within there you would also have to choose which of the quantities are uncertain and so relevant for the problem that we explicitly have to look at them in probabilistic terms and for example, do statistical analysis on them. Then you have to establish your reliability requirements. You can assess that reliability index, but you also need a target value to adhere to. That's what happens in that first stage. In the second stage, you go through uncertainty characterization into the topics mentioned in the beginning. So the geotechnical units and the parameters, the actions, the groundwater and the pore pressure conditions, and also the model uncertainties involved. And then in the third stage, you select the reliability method. You estimate your probability of failure, and we give some more material on checking your results and making sense of the results of the analysis. In the end, you get a reliability index out of the procedure, you compare it to your previously established target value, and that is your verification. What are typically the benefits, talking from, let's say, the experience that we have from projects on working with reliability-based methods? We can often achieve more cost-effective designs. You can have extension of or substantiation of residual service life of existing structures. You can substantiate, for example, the safe change of use of existing structures. I'll show you with some examples what I mean by that. And the results can directly feed into risk management and maintenance because you have a more nuanced information than just okay or not okay. And how do we get that? Typically it's by a more accurate way of assessing reliability compared to the generalized design approaches. You just have to imagine that partial factors, the partial factor sets that we use are used for such a wide range of conditions and structures. If you go into more detail, sometimes you just overshoot with the safety that you have, and sometimes you undershoot with the safety that you have. And if you can look into that with more detail, you can get a more accurate estimate. You avoid over-conservatism in many places where you would stack a lot of cautious choices, and you have the possibility to incorporate performance data or monitoring data by using Bayesian analysis. So that is, for example, using the information that a structure has survived certain load conditions, which is harder to do in another setting. To give you some examples, so for the Netherlands, where I come from and have worked in the field of flood defenses for a long time, our motivation to get started with these techniques was that we had a new code, and the safety requirements were actually presented and formulated in terms of acceptable probabilities of failure or flooding for the different flood defenses as represented by the colors here on the map. And we developed a whole set of tools and guidelines which would allow for the use of probabilistic analysis to assess those probabilities of failure or flooding of the different parts of the flood defense system. Now, that is not to say we always use probabilistic assessment for this. The probabilistic version is, or the reliability-based methods are used side by side with partial factors, and typically reliability-based methods are used when the stakes are high. So if your normal design produces a stability berm of a river levee that would lead to the demolishing of the adjacent houses, and you really want to have a closer look if that berm is needed, that would be a typical case. So there it's also more the special occasions, but the tools are there. In other applications, application examples for design are, for example, like with the flood defenses that I just showed, for some structures you just have requirements already stated in terms of acceptable probabilities of failure. Nuclear power plants, in this example we worked on a couple of LNG tanks in the port of Rotterdam, and these structures just had these requirements, and we had to show acceptable levels of risk or probability of failure. Other examples that you see are design optimization. We've seen, for example, we've seen examples of monopile design, for example, by NGI, where you see that the length of a monopile can, of course, be a large cost factor, and then you want to really be able to optimize and use all the data that you have. We've seen examples in temporary structures. Just recently in the Netherlands we had cases where there had to be working platforms for machines, and with the conventional set of partial factors they could really not make the working platforms work. And then we had a closer look and then substantiated a different set of partial factors, and when you dive deeper into the topic you see that the generalized set of factors, as I mentioned at the beginning, sometimes is just way off for what you would need for that particular situation. Now to the assessment of existing structures, particularly interesting. One of the clients that we work for is the Port of Rotterdam, with a large portfolio of quay walls. And they have a lot of structures approaching the end of the original design lifetime. 50, 60, 70, 80-year-old structures, concrete and steel, subject to corrosion, and then there are questions arise about the residual service life, the safe operation of the structures, and oftentimes also change of use. Can we deepen the harbor basin still by a meter, which would increase the retaining height? Can we use different loads on the cranes, surcharge loads on the structure itself, and so on? And if you go into that problem, let's say calculating the safety of the structure with a code meant for design of new structures, very often the only thing that you can conclude is that we wouldn't have built the thing now as it is standing there, and you don't get any further than that, right? Because you actually get very low safeties for that existing structure. But does that actually mean that it has no justification of being operated at the moment? How long can you do it? And what about these questions of change of use? And there also these advantages of reliability-based methods of combining different sources of information, performance data come into play. Very similar question for railway embankments, also mostly built around the end of the 19th and beginning of the 20th century, I think, in most of Europe. And the trains are operating just fine, but now we want to extend the use of the network in terms of faster trains, higher frequencies, heavier trains, and so on. And again, if you look with new design codes, you couldn't do anything, and then you have to have a more specific look at the situation. So there we also use the benefits of reliability-based methods. An example from Amsterdam. Similar type of problem, maybe different benefits. You have foundations of the old bridges in Amsterdam, also 200 to 300 years old. The wooden pile foundations are subject to bacterial degradation. You have limited inspection data on how much that degradation has progressed and on the actual state of the foundation. And then you have to say something with a limited amount of data. So you could say, why look at it at all? Because sometimes they actually collapse, and so questions arise about just the safe sure if you call it operation in a sense, but if they can safely be used in the inner city of Amsterdam. So there we also went with a probabilistic approach to combine data from the whole city on the piles with local information and the reliability based approach for the safety of existing structures. And lastly, I just want to touch upon the topic of partial factors and their relation to reliability. As I said here earlier, the partial factors are actually there to ensure a sufficient degree of reliability. I think there is in general, two ways to look at it. You could look at it from the sort of empirical perspective that our partial factors at the moment seem to be okay because we don't have too many collapses and problems and failures to adjust anything. But the other thing is also you can look at it from a reliability point of view, especially in terms of where to put the safety, right? Absolute safety levels may be a different question, but where to put the safety and how much. And there are approaches to approach the substantiation of partial factors from a reliability point of view. What you typically do is you do the normal design calculations side by side with reliability, and you look at, with different sets of partial factors, how the reliability levels turn out and how do you achieve your desired level of reliability. So in the guideline we provide the, let's say, the underlying concepts and we describe the approaches on how to do partial factor assessment with reliability concepts, which could help national standard bodies in choosing partial factors or substantiating changes in the national annexes. And it could also be used in a project-specific setting where you say we adhere to a reliability-based approach, but we also want to produce in parallel the information on the partial factors that implies. So in the guideline we have examples on, on how you do the reliability analysis, but some of the examples, like this one here on pile design using the model pile method with a larger CPT data set from Amsterdam, also shows you the side-by-side comparison of the partial factor approach and the full reliability version, and it gives you an idea of this calibration of partial factors, which would now a little bit too much to go into detail, because we want to jump right into that design example that we have. So now Stefan will first introduce the design example for us, and then we will go through the example by just giving you a block of, let's say, theory or things that are said in the guideline, what you should do, and then Stefan will come back and tell you how that was used in the example. And as such, we will go through it.